installs using next-generation computers. The 8-bit part has 62 contacts located in the slot.
CPU are small components that carry out all the instructions for every program you run. These components include AND gates, which only allow electricity to flow to their output wire if all their input wires are on. The AND gates use tiny transistors to control the flow of electricity to the output wire. The electricity from another part of the computer flows in from the top and gets stopped at the first transistor unless its input wire is on. When that input wire turns on, it causes an electric field to form around a small piece of insulated metal. This electric field reaches out past the insulation and causes the properties of the semiconductor material below it to change, turning a small part of that semiconductor into a full conductor, bridging the gap for any electricity flowing in from the left and out to the right. The types of components you create from transistors are based upon how you wire their inputs and outputs together. If you chain them together so that the output of one flows to the input of the next, then you are creating an AND gate, where all the input wires must be on for the final output wire to be on. Inside the Scott CPU, you'll see a number of these AND gates scattered around, with some having more inputs than others. Another type of component that you'll come across is the OR gate, which is represented by this shape. Instead of chaining the output of each transistor to the input of the next, you instead run all the output wires to the same place, the output of the whole gate. In this way, if any of the transistors have their input wire on, then electricity flows straight through them to the gate's output. You'll also see a number of these OR gates scattered around the Scott CPU. By the way, the Scott CPU comes from the book But How Do It Know by John Scott, which is available at his website, buthowdoitknow.com. It includes a great explanation of how computers work for beginners, and John was kind enough to allow his CPU design to be used in this video. The other basic component you'll see in any CPU, including the Scott CPU, is the NOT gate. The NOT gate uses a transistor to divert the electricity already flowing to the output of the gate to a ground wire, effectively short-circuiting the output wire, turning the output of the gate off if the input wire is on. There are a number of these NOT gates inside the Scott CPU, not only in the locations seen here, but also inside the other components. For instance, the stepper component is just a particular combination of AND, OR, and NOT gates, where the output wires turn on in sequence each time the input wire to the stepper turns on. This input wire comes from another small component called the clock, where the output wires turn on and off again very quickly in a steady pattern. The only other component used in this part of the CPU is the selector, formed from another combination of AND, OR, and NOT gates that turn on one of several output wires depending upon what input wires are on at the moment. In another area of the CPU is the arithmetic logic unit, which includes more AND, OR, and NOT gates, along with the selector component that we just saw. There are a few other components in the ALU, like the exclusive OR and the NOR gate, but these are just made from the same OR gates we saw earlier, along with some AND and NOT gates. In other videos, we'll see how these components work together to process instructions sent to the CPU. This has been a brief look at what's inside the CPU. The first component is the control unit, which is kind of like a captain in the Army. It receives its orders from RAM in the form of an instruction, and then breaks that instruction down into specific commands for the other components. One of the most important components under the command of the control unit is the arithmetic logic unit, or ALU for short. The ALU is what performs all the mathematical operations inside the CPU, such as addition, subtraction, or even comparison like we saw earlier. The arithmetic logic unit has two inputs. We'll label them input A and input B, and assume they are two numbers from some previous load instructions. Now we might want to add those two numbers together. The control unit receives that instruction from RAM and then tells the ALU what type of operation to perform. The ALU performs the operation and then outputs the answer. Sometimes, though, depending upon the type of instruction, the output from the ALU can actually be ignored. For instance, if you have a compare instruction, the ALU doesn't need to output an answer. Instead, it just needs to tell the control unit how the two numbers compare to each other. For this, the ALU uses what are called flags, and they help the control unit decide what to do when it receives the next instruction, like jump if, which we'll see later. For now, though, let's say that we are working with an instruction that does produce an output. Where does that output actually go? Well, the 8 wires coming out of the ALU would actually run to what is called a register. A register is a very simple component whose only job is to store a number temporarily. Registers act just like RAM, except they are inside the CPU, making them faster and more useful for storing a number temporarily while an instruction is being processed. When the ALU sends the output to the register, it won't actually be saved until the control unit turns on the register's set wire. The set wire is just like the one we saw earlier for RAM. When the set wire is turned on, the register saves whatever number is on its input wires. Once we have the output saved in the register, though, how do we get it back out? Well, when we are ready to move a number out of the register, we need another control wire called the enable wire that also runs from the control unit to the register. As soon as the control unit turns the enable wire on, the register will output whatever number is saved inside. The output wires of the register then connect to what is called the CPU bus. A bus, as we saw earlier on the motherboard, is simply a group of wires that connect multiple components inside a computer. On the bus are some other registers with their own set and enable wires. These may have numbers from previous instructions already saved inside. So the control unit will then turn on the set wire of the particular register that it wants to save that number to, and that number will be saved in that register. Afterward, the control unit will then turn off the enable wire from the first register and clear the bus. The 4 registers at the top are just used for storing numbers between operations, so they have output wires that go directly back onto the bus. So now we have moved a number from one register to another just by turning some wires on and off. That's the advantage of the bus, easily moving numbers between components. The disadvantage of the bus is that you can only have one number on it at a time. Because of this limitation, the arithmetic logic unit uses a temporary register for input B. When the control unit is processing an instruction involving the ALU, it will move one of the inputs to the temporary register. The temporary register has no need for an enable wire since it only outputs to the ALU and doesn't conflict with any other registers. The other input to the ALU comes directly from the bus. The control unit will enable another register, and that number will become input A to the ALU. That number stays on the bus until the ALU is finished processing the instruction. And so now there are 2 inputs to the ALU, and we're ready for the ALU to perform an operation. As we saw earlier, the control unit knows what operation to tell the ALU to perform because of the instruction it receives from RAM. The instruction itself is in another register called the instruction register. By the way, the input wires from the bus won't affect this register since the instruction was already saved in a previous step. This register, like the temporary register, also has no need for an enable wire since it just outputs to the control unit. Based upon this instruction, the control unit then tells the ALU what type of operation to perform. So let's say the instruction we're processing is a compare instruction. With the compare instruction, we're not interested in the number that is output by the ALU. We only want to know how the 2 inputs compare to each other. For that, we use the flags that we talked about earlier. Each flag is just a wire that turns on or off depending upon whether or not a certain condition is true. Inside the Scott CPU, there are 4 flags, and we'll look at 2 of them now. The A is larger flag will turn on if input A is larger than input B. If the inputs are the same, then the equal flag turns on, and if both of these flags are off, that means input B is larger. But in this case, the equal flag is on, so that means both inputs are the same. Once the compare instruction is over, we still need to use the flags for the next instruction, so we'll save them to a register that only has 4 inputs and 4 outputs, 1 for each flag. Once the flags are set into the flags register, the CPU is finished with the compare instruction, and it can then request the next instruction from RAM. Generally, the next instruction after a compare instruction is a jump if instruction. This combination of a compare and a jump if instruction, by the way, is very common in computer programming. Anytime there is more than one possible path through a program, the computer is using these instructions to tell it which way to go. So now that we're finished with the compare instruction and our flags are saved in the flags register, we need to tell RAM that we're ready for the next piece of data, in this case the next instruction. So inside the CPU, another register that is very important is what's called the instruction address register. The CPU uses this register to know where the next instruction should come from in RAM. When the CPU is ready for the next instruction, it enables the instruction address register onto the bus. Eventually, the instruction address will flow to RAM, but it doesn't get there directly. There is an intermediary register called the memory address register, whose only job is to tell RAM what memory address the CPU wants next, since it won't always be an instruction. Once the instruction address is set into the memory address register, it is automatically sent to RAM since the memory address register doesn't have an enable wire. The control unit then turns on the enable RAM wire, and RAM automatically sends back the data at that address, which in this case is an instruction. That instruction is then saved in the instruction register, and the control unit begins processing it. In this case, it's a jump if equal instruction, which checks to see if the equal flag is on. It does that by running one of its wires and the equal flag wire into an AND gate. If both inputs to the AND gate are on, then the output wire turns on as well. This output wire will then trigger the jump. That jump eventually retrieves the next piece of data from RAM, which happens to be an address, and move it into the instruction address register. When the jump if equal instruction is over, the CPU then processes the instruction at that new address. At that new address may be some instructions that output the text "you guessed correctly" onto the screen, because now we know that the user guessed correctly. So we'll add the final 4 wires to our CPU, which are used to control the external devices like the monitor and the keyboard. We now have a nearly complete picture of what the Scott CPU looks like. Data moves around inside the CPU using the bus and is stored in each register according to how that data is going to be used. Each instruction that we have seen can be processed by the Scott CPU in about 6 clock ticks. Modern CPUs can process multiple instructions per clock tick, meaning that the computer you're using to watch this video is likely processing tens or even hundreds of billions of instructions per second. That phenomenal speed is accomplished by using more than one of each component and making sure that all the components are active as much as possible. This makes modern CPUs much more complicated than the Scott CPU, but they are still fundamentally doing the same things as the Scott CPU. So now let's zoom back out and we can see all the wires that run back out to the pins on the chip. On the right are the set RAM and enable RAM wires. On the top are the RAM address wires. On the bottom are the data wires that run to both RAM and the external devices. And on the left are the input-output control wires. So let's zoom back out to see the rest of the chip, and we'll put the cover back on the CPU.
Hello everyone, and welcome to this video. We're going to be talking today about what a register is. We're going to have a couple examples. I'm not going to explain all of them for lack of time, but the most basic function I will describe and define on those. So what is a register? A register is basically a group of flip-flops that are hooked together to hold certain aspects of data. So usually we're going to use in D flip-flops in the examples that we have here, but I guess that is what a register is. Now, what do we use a register for? A register, like we said, can be used for data storage, so we can use it to store data for further use. For instance, you can hold numbers in order to add them later, subtract them later, multiply them, or even display them on a LCD, for instance, if you have that kind of programming in your circuit or your processor. Data can also be transferred. Due to the fact that it is stored, it can be transferred from one register to another without losing the data. Now let's see a couple examples of registers in order to see what they do. These are one of the more simpler ones. We have, remember in these flip-flops, each bit requires a flip-flop, and in each flip-flop, in this case, Q follows D. Of course, in the shift to the left example, you can see that the first D follows Q, but that Q follows the last D. So it's really not that complicated of an issue. It's just Q will always become what D is. So D is the first state, and then you input it, and then Q outputs that. So we put in our first input there, and now we have the most significant bit to the least significant bit, which is x0. Remember, the clock does not affect really whether it shifts from left to right. It is the hookups between the D's and the Q's here. Now let's look at this register. This register is a loadable 1-bit register in that it has an input, the DN. It has a load switch that says, do I want to load the old value, or do I want to load in the new value? If load is 0, then it's going to take that Q, which is this is the old value, the register with the old value, and it will take that and will say, okay, so that is the old value. Let's put the old value back into that register. Just keep cycling through. If it's 1, you're going to say, you know what? I kind of want this guy loaded in there, and that is going to be contained there, and it will wait for you to, it'll cycle back, and now it'll wait for you again to say, okay, do you want to load that new value back in again, or do you want to put an even newer value in? Now, once again, registers aren't the most complicated thing in the world, but they can get pretty complicated when you reach the capacity of a register file. So let's talk a little bit about that. A register file is an array, or basically kind of a string of registers together in one unit. So it can contain multiple numbers, and these numbers are going to do different things. They can be held together for math equations or for displays, as we said before. Here's an example. I couldn't really give you gate level just because this may become part of your final, and I don't want to give too much away there. But here we have a register file. We have 2 registers. Each register will hold a 4-bit, as we see from D0 to D3, it will hold a 4-bit number. And we see that the clocks are connected, and there is a write enable switch, which will allow it to be manipulated or moved or printed out on an LCD screen, or sorry, display. And those are the outputs. Now, generally, a register is going to be ALUs and muxes and other things are going to have registers because they also need to store data. But a register file may receive data that is stored in those functions and then be used to either be spit back into those functions, or it will be used in order to be shot to a display or just held there. For instance, if I were to have an ALU will have a register because it needs to hold a number. In the case of multiplication or something like that, it will need to have its own register file to store data. But let's say I want to take from the ALU and I want to spit into the register a 3, let's say, and I have a 6. So I would load a 3, and I would get a 3 from the ALU, and I would add the 2 3 with the ALU, making a 6, and then I would say, okay, you know what, I want to load the lower register with a 6, and I want to load the higher register with the same value I had before, and I will we'll spit that number to the ALU and add that together. 3 plus 6 would be 9, and that way you can do even multiplication if you want. You can do addition, subtraction, all through the simple use of a register file and an ALU. You would obviously need a mux for a bridge point, but that's kind of besides the point. Just remember, registers are for holding data, 1 flip-flop per bit. They can contain several options, including write enable, They can include uh, a load function, an enable input function, a shift enable, and it really depends on the way that you'll design them. But just remember that what they're for is storage, and what they're used for is data transfer and storage, and that they all need to be on the same clock, and that D will follow Q in most cases. And I guess the best way to learn about them is just kind of using them and playing with them in Xilinx, which you probably won't have a ton of time for, but in the labs you will be able to learn what a register does and a register file does in your final lab. So good luck to all of you, and I hope this has been of some help. Registers are definitely going to be a useful thing in your career, whether it be in software design or hardware, whatever. So try and pay attention to this part of the course.
MID is the processor register. In computer architecture, a processor register is a small amount of storage available as part of a CPU or other digital processor. Such registers are addressed by mechanisms other than main memory and can be accessed more quickly. Almost all computers, load store architecture, or not, load data from a larger memory into registers, where it is used for arithmetic, manipulated, or tested by some machine instruction. But cache is without doubt the most important thing you can have in your processor. It really does improve the performance of your system. Let me show you how it does it. Now we have a good little diagram here. There is processor, cache, cache controller and RAM. The cache can do something called reading ahead. Let me describe you what does that mean. Here in RAM, files are broken into little blocks, generally into 64 kilobytes blocks of RAM. Let's imagine we have opened a file, and we start reading it. The first thing the CPU does is to search for the file in cache, but of course the cache doesn't have it. That is called a miss. So in the second process the CPU goes to RAM and finds it in there, but it can bring over only one block at a time. So it grabs hold of that block, transfers it back to the CPU, and it starts working on it. And this is where the intelligence kicks in, because the cache controller makes a very good assumption that if I use that particular piece of code related to that file, I might need the rest of the code related to the file at some point very shortly in the future. So the cache controller grabs hold of the rest of the file and moves it to the cache. When indeed the CPU needs to find the rest of the information, it searches first the cache, and it finds it in there. That saves it from having to go to RAM at all. The main question here is why the CPU just doesn't go to RAM, and there is a very simple reason for this, because cache is much faster than RAM. Now you remember that blocks of code is moved from RAM to cache, and that's where the replacement policy decides where in the cache a copy of a particular entry of main memory will go. But when the cache is full, a replacement algorithm must choose which items to discard to make room for the new ones. If the replacement policy is free to choose any entry in the cache to hold the copy, the cache is called fully associative. At the other extreme, if each entry in main memory can go in just one place in the cache is direct mapped. Let's begin with fully associative mapping. Its approach is to store both memory address and data together in the cache. A fully associative cache requires the cache to be composed of associative memory holding both the memory address and the data for each cache line. The incoming memory address is simultaneously compared with all stored. If a match is found, the corresponding data is read out. Single words from anywhere within the main memory could be held in the cache, if the associative part of the cache is capable of holding a full address. In all organizations, the data can be more than one word, that is, a block of consecutive locations, to take advantage of spatial locality. In the figure, a line constitutes 4 words, each word being 4 bytes. The least significant part of the address selects the particular byte, the next part selects the word, and the remaining bits form the address compared to the address in the cache. The whole line can be transferred to and from the cache in one transaction, if there are sufficient data paths between the main memory and the cache. With only one data word path, the words of the line have to be transferred in separate transactions. The fully associate mapping cache gives the greatest flexibility of holding combinations of blocks in the cache and minimum conflict for a given size cache, but is also the most expensive. It requires a replacement algorithm to select a block to remove eponymous, and the algorithm must be implemented in hardware to maintain a high speed of operation. As we said, there is another mapping method called direct mapping. The fully associative cache is expensive to implement. In direct mapping, the cache consists of normal high-speed random access memory, and each location in the cache holds the data at an address in the cache given by the lower significant bits of the main memory address. This enables the block to be selected directly from the lower significant bits of the memory address. The remaining higher significant bits of the address are stored in the cache with the data to complete the identification of the cache data. Consider the example shown in the figure. The address from the processor is divided into two fields, a tag and index. The tag consists of the higher significant bits of the address, which are stored with the data. The index is the lower significant bits of the address used to address the cache. When the memory is referenced, the index is first used to access a word in the cache. Then the tag stored in the accessed word is read and compared with the tag in the address. If the two tags are the same, indicating that the word is the one required, access is made to the address cache word. However, if the tags are not the same, indicating that the required word is not in the cache, reference is made to the main memory to find it. For a memory read operation, the word is then transferred into the cache, where it is accessed. Here is the direct map cache with a line consisting of more than one word. The main memory address is composed of a tag, an index, and a word within a line. All the words within a line in the cache have the same stored tag. The index part to the address is used to access the cache, and the stored tag is compared with required tag address. For a read operation, if the tags are the same, the word within the block is selected for transfer to the processor. If the tags are not the same, the block containing the required word is first transferred to the cache. There is a third type of mapping called set associative mapping. Its scheme combines the simplicity of direct mapping with the flexibility of fully associative mapping. It is more practical than fully associative mapping, because the associative portion is limited to just a few slots that make up a set. The organization is shown in the figure. The cache is divided into sets of blocks. Each block in each set has a stored tag which, together with the index, completes the identification of the block. First, the index of the address from the processor is used to access the set. Then, comparators are used to compare all tags of the selected set with the incoming tag. If a match is found, the corresponding location is accessed. Otherwise, as before, an access to the main memory is made. The tag address bits are always chosen to be the most significant bits of the full address, the block address bits are the next significant bits, and the word address bits form the least significant bits, as this spreads out consecutive main memory blocks throughout consecutive sets in the cache. Notice that the association between the stored tags and the incoming tag is done using comparators, and can be shared for each associative search, and all the information, tags, and data can be stored in ordinary random access memory. The number of comparators required in the set associative cache is given by the number of blocks in a set, not the number of blocks in all, as in a fully associative memory. The set can be selected quickly, and all the blocks of the set can be read out simultaneously. After a tag has been identified, the corresponding block can be selected. The replacement algorithm for set associative mapping considers the lines in one set, as the choice of set is predetermined by the index in the address. Hence, with two blocks in each set, for example, only one additional bit is necessary in each set to identify the block to replace. Now let's talk a bit about the problems that occur. When a data is written to the cache, it must at some point be written to the RAM as well. The timing of this write is controlled by what is known as the write policy. In a write-through cache policy, every write to the cache causes a write to the RAM. Alternatively, in a write-back cache, writes are not immediately mirrored to the store. Instead, The cache tracks which of its locations have been written over. These locations are marked dirty. The data in these locations is written back to the RAM when those data are evicted from the cache. For this reason, a miss in a write-back cache will often require 2 memory accesses to service, one to retrieve the needed data, and one to write replaced data from the cache to the store. The probability that the required word is already in the cache depends upon the program and organization of the cache. Typically 70 to 90% of references will find their words in the cache, called a hit, but the rest is when a reference to the main memory is necessary, called a miss. The hit ratio of a cache describes how often a searched-for item is actually found in the cache. More efficient replacement policies keep track of more usage information in order to improve the hit rate for a given cache size. The latency of a cache describes how long after requesting a desired item, the cache can return that item when there is a hit. Faster replacement strategies typically keep track of less usage information. Or, in the case of direct mapped cache, no information at all, to reduce the amount of time required to update that information. The average memory reference time, as you can see, is a sum of the miss ratio multiplied with the time to make access to RAM, plus the time to reference the cache, if there is a